Have you ever had a hunch about something but wondered how you could actually prove it? How do we get from a simple gut feeling to a decision that's backed up by cold, hard facts? Well, today we're diving into the powerful framework that does exactly that.
It's the fundamental question, isn't it? Whether you're a scientist testing a new drug or an entrepreneur launching a new feature, you're always facing this challenge. How do you know if what you're seeing is a real effect or just random chance?
The answer, it turns out, is to use a structured scientific process. This is a method that powers some of the most critical decisions that affect our lives every single day, and it takes us way beyond just making a guess and hoping for the best.
That method is called hypothesis testing. This is the statistical engine that researchers use to see if a new treatment actually works. It's what companies like Netflix and Amazon are doing constantly behind the scenes. They don't guess if a new layout is better, they test it. And this is exactly how they do it.
To really wrap your head around this, I want you to think of it with a simple but honestly a really powerful analogy. Imagine that hypothesis testing is basically a court trial, but for data. You've got a defendant, a prosecutor, evidence, and of course, a final verdict.
Okay, this right here is the key to the whole thing. In a courtroom, what's the golden rule? The defendant is presumed innocent until proven guilty. Well, in our data trial, we have the same kind of default assumption. It's called the null hypothesis, and it basically says nothing's changed, there's no effect. Our new idea, that's the alternative hypothesis. It's like the prosecution's claim of guilt. Our job is to collect enough data, enough evidence, to see if we can overturn that default innocent verdict.
And this isn't some chaotic process. No, scientists and data analysts follow a very clear 5-step framework to make sure this data trial is conducted fairly every single time.
These 5 steps are pretty much the universal roadmap. You start by clearly stating the two competing ideas. Then, you decide upfront how much evidence you're going to need to be convinced. After that, you go out, you collect your data, you calculate how strong that evidence is, and finally, you make the call.
So what is that threshold for evidence I mentioned? It's called the significance level, or alpha, and usually it's set at 0.05, or 5%. What this really means is that we're willing to accept a 5% chance of being wrong, of accidentally convicting an innocent null hypothesis. You can think of it as our standard for beyond a reasonable doubt in the world of data.
And this brings us to the star of the show, the p-value. The p-value is your main piece of evidence. It answers one simple question. Assuming the default idea is true, how weird are my results? So a really tiny p-value means your results are super surprising, which, makes you start to doubt that default assumption in the first place.
Okay, theory is great, but let's see how this thing actually works in the wild. We're going to take this 5-step framework and apply it to a really simple, real-world claim.
So here's our case. We've got a light bulb company making a very specific promise. But are they telling the truth? Let's you and I put their claim on trial.
All right, so here's how we set up the trial. Our null hypothesis, the innocent plea, is the company's claim. The average is 1,000 hours. Our alternative hypothesis is that, it's not 1,000 hours. So we go out, we test 30 of their bulbs, and we find they only last 980 hours on average. Now the big question is that 20-hour difference a real thing, or could it just be a random fluke?
After we run the numbers through the right statistical test, we get our evidence, the p-value. And in this case, it turns out to be less than our 0.05 significance level. This means getting a result like 980 hours is really, really unlikely, super surprising if the true average was actually 1,000.
And that leads us to the verdict. Since our evidence, the p-value, is stronger than the threshold we set, we have to make the call. We reject the null hypothesis. The data gives us enough evidence to say that the company's claim probably isn't accurate.
But wait, there's one last absolutely critical distinction we have to make. Honestly, this is what separates someone who kind of gets data from someone who truly understands it. And it all goes right back to our courtroom analogy.
This is so important, I can't stress it enough. What if our p-value had been large? What if we didn't have enough evidence? In that case, we would fail to reject the null. But, and this is the key part, that is absolutely not the same thing as proving the company's claim is true. And this is why the analogy is so perfect. A not guilty verdict doesn't mean the person is innocent, right? It just means the prosecution didn't bring enough evidence to get a conviction. It's the exact same thing here. Failing to reject the null just means our test wasn't powerful enough to make a strong case against it.
So, now you have the framework.
It's a powerful tool for cutting through all the noise out there and making decisions based on actual evidence. It really makes you wonder if you could put any common belief, any popular claim that you hear all the time on trial, what would you choose to test first?